Okay. Okay. Yeah.
In getting involved in the field, strongly encourage you to come to our events. Well, you should do that anyways. But yeah, we're the space for you. If you need to use the washrooms, just outside the glass doors. If you need to come back in, please use the pin pad just above the pin, which is written just above the keypad. Also, for today's presentation, we're going to be using Slido to collect questions. So if you look around the walls, there's some orange posters with a QR code. I strongly recommend you scan that QR code. It'll just take you to a URL where you can submit questions. So we ask that you don't raise your hand and ask questions during the presentation. If there are quick questions I see on Slido relevant, I may interrupt Maaz. If not, we're going to let him do his whole presentation all the way through, and then we can vote on questions, and there will be a little Q&A at the end. So yeah, would strongly encourage everyone to use Slido. And yeah, if you're watching this stream online, you are also welcome to do so. There should be instructions in the video. And without further ado, let's give a big warm welcome to Maaz Mohammed.
All right. Wait, Georgia, can I go back to the title? Oh. Okay. Yeah, I just wanted to. Sorry, I just wanted to spend some time talking about what the overall project is first, before I get into the details. So, yeah, I guess I'll start with introductions. So, hi everyone, my name is Maaz. I'm an Anthropic fellow. This is the project that I've been working on at Anthropic for the last few months. These are my co-authors. So Liam, he's at Northeastern University, and Zach and Nicholas are my supervisors at Anthropic. I'm sure many of you have heard of Nicholas. He's quite well known in the cybersecurity space, and Zach is quite well known as well in the safety space and the Python open source community. So basically, the inspiration for this project was that many people know that LLMs are increasingly very good at code understanding. And at the same time, agents built on LLMs are increasingly autonomous and so on. And so this presents some unique risks as well as some unique capabilities. So for example, this morning actually, Anthropic published a report about a large-scale cybersecurity attack that they discovered that was using Claude Code, which is Anthropic's coding agent. And basically, it was the cyber attack was almost entirely autonomous. There was some light human supervision, but essentially the agent was doing it by itself, and it was scaling up by itself, and so on. So actually, I will present a very similar agent today, but for some good use. But obviously, in any security domain, there's the problem of dual use, which I will talk about as well. So okay, so now let's talk about some details. So the idea here is that we're going to leverage something called property-based testing. And property-based testing is a paradigm of software testing, which basically aims to verify whether some code satisfies a property over an input domain. For example, you may want to say that, okay, for all integers, my function does this, or it satisfies some property. Now, how property-based testing works is once you write this out and you pass into a property-based testing framework, it basically performs randomized testing. So the input domain that you specified, it just spams like hundreds or thousands of inputs that are from that input domain, and it checks that those properties hold. Now, obviously, because it's testing random inputs, if it finds a counterexample, so if it finds an example that breaks your property, then for sure your property does not hold. It doesn't hold over the entire input domain. However, if all cases pass, you actually don't know rigorously whether the property holds or not, because you may have just not drawn the counterexample. Now, this is in contrast to formal verification, which is much stronger. In formal verification, you do the same thing where you verify that code satisfies some property over an input domain. But in formal verification, it can tell you whether the property holds or not definitively. And it doesn't use randomized testing. It basically uses some like mathematical algorithms, like for example, proving some set of inequalities is not feasible, this sort of thing. However, formal verification is much more difficult to do, much less scalable. Its computational complexity is horrible. And it can't verify all the possible properties that we may want to verify because there's some limits to its expressivity. On the other hand, so that's like more formal than property-based testing is formal verification. Less formal or less rigorous than PBT is example-based testing or unit testing, which is what pretty much every programmer knows and is taught to do. And that's essentially where I write out specific test cases and I test whether the property holds for them. So here's a comparison of them. Wait, one sec. Okay. Oops. I don't know what happened there. Oh, okay, it's back. Yeah. Okay, there we go. So here's an example. Suppose I have a function. I've written a sorting function, and I'll call it mySort. So the way that I would approach this testing under the two different paradigms, so in example-based testing, I would write out explicit lists. So of course, if my sorting function works, then the sort of 3, 2, 1 is 1, 2, 3. Or the sort of 10, 17, 12 is 10, 12, 17. In property-based testing, I don't write out specific examples. Instead, I have to specify basically two types of information. The first information is the input domain. So this code is in Python. It uses Hypothesis, which is basically the property-based testing library for Python. And in fact, my two co-authors, Liam and Zach, are the chief maintainers of it. So that was a big help. So in Hypothesis, you would add this given decorator above the function, and then you write out what types of inputs you want the hypothesis framework to draw when you run the test. So this is basically saying I want lists of integers. And Hypothesis, or this like given decorator, actually comes with a lot of primitives, a lot of options, and is highly composable, and you can like make all sorts of inputs, generate all sorts of inputs that you want. Then inside the testing function, I would just have assertions just like any other Python test. So in this case, I'm just testing the property of being sorted. Or namely, I'm just testing that the list is non-decreasing. So I'm just looping through the list, and I assert that result I is less than or equal to result I plus 1. So when I pass this into the PBT, into Hypothesis, it'll just generate like thousands of lists of integers. I can bound the size of the list. I can bound the range of the integers, etc. There's a lot of options to do. So this is basically the two philosophical approaches to testing. Oops. Okay. Okay. There we go. Now, some common properties to test. These basically look like properties of functions that you would see in math or in abstract algebra. So, for example, one of the common properties to test, one of the most powerful properties, is the round trip property. Essentially, that f and g are inverses of each other. So this appears quite often because, for example, you may have an encode and decode. Obviously, you know, if you do them both, you should get back the original information. Or if I write to a file and then read from the file, I should get back the original thing. So this is one of the most powerful properties, I would say. And this can often bring up strange bugs that you may not have anticipated. Another common one is idempotence, meaning that if I apply the function again, it has no effect. So if I apply the function twice, it's the same as applying it once. A great example of this is sorting, right? Because if I sort it, then I call sort again, it's already sorted, so it's not going to do anything. Sometimes there are invariants which are specific to the application. So for example, maybe I'm writing some geometry package, and so lengths should always be non-negative. If I calculate the perimeter of a polygon or something, it should always be non-negative. And then, you know, functions can commute or be associative, meaning that the order of the order of the inputs doesn't matter, or the order of applying multiple calls doesn't matter. And of course, you can brainstorm like dozens of other properties depending on your specific application. But these are just some of the common properties that people like to test. Now, in practice, property-based testing is very useful because it covers edge cases that the developer did not think of, right? So in unit-based testing or example-based testing, the developer has to sit down and think through strange cases or where bugs could possibly arise. Now, it's not possible, I think, for a developer to think through all of these edge cases, because for example, if they had already thought of those edge cases, they likely would have already written code that covered those edge cases. However, on the other hand, I think the reason why PBT is not that popular is because it's quite, I think it requires a higher level of abstract thinking in the sense that you need to think more deeply about your code and need to think more deeply about what properties you're trying to satisfy and so on, especially if you're trying to test multifunction properties, like for example, the very famous round trip property, then you really need to know your code well. You also need to know like which inputs you should allow and so on. So this gets quite difficult to think about. So the idea that we had here is, as I said in the beginning, LLMs are increasingly very strong at code understanding. And so we thought, can we get an AI agent to autonomously infer the properties of code and test them? And explicitly, we were trying to get the agent to find bugs, but you can also slightly modify it to just be like a helpful developer tool and just like write good tests. But in this presentation, I'll be talking about an agent that is explicitly told to try to find bugs. So our agent is built on top of Claude Code, which is Anthropic's coding agent, as I mentioned in the beginning. And it essentially takes a single argument, which is just its target. So you can tell it to target a file, like a .py file. You can target a module, like let's say numpy.linalg. Or you can target a specific function. Obviously, if you target a file and module, you can get much more rich properties, because then you can get the multifunction properties. If you target a function, you basically just get the single function properties. So the agent workflow is basically these steps. So I'll go through them in detail. The first thing is, once the agent is given its target, it has to analyze and understand the target first. And it can do this by gathering various information about the target. So for example, it reads through the code base, it reads the documentation, it tries to find source code, which may not be immediately obvious. So for example, in some Python code, the real source is in C files. So the agent will also try to find these C source files. It can read things like type hints, for example, in order to get an understanding of what input domain it should specify. For multifunction properties, it tries to understand the context of the function, in the sense that sometimes, for example, if you have some like inner helper function, these things are not properly documented often. However, you can get a sense of what the proper input domain is of these functions by looking at which function calls it and under what circumstances it's called and so on. So it's told explicitly to like go find all of this information. Once it thinks that it has a good understanding of the code base, it then proposes properties. What should be true of the code? So it can propose properties like idempotence. It can propose like mathematical properties, for example, like all outputs should be non-negative, and so on. So it writes out this list of properties. It then translates these properties into hypothesis. Now there's two things going on here, right? So it has to write out the properties into assertions, but it also has to keep track of the proper input domain. Because of course, if you have an incorrect input domain, you can either get a task failing or passing, but it shouldn't actually fail or pass. Now, this is really the agentic part of the workflow, is this loop here. This loop here is basically running the hypothesis tests and then reflecting on the PyTest output. And I'll go into more detail about this, but essentially it does analyze both the passing tests and the failing tests, because either of those can be injustifiably passing or failing, right? Which I'll talk about some examples of that. Now, if it thinks that some modification to one of the tests has to be made, then it goes through this loop. So it again like rewrites the test and it runs it again and so on. Now, this agent was specifically created to find bugs. So eventually, if it convinces itself that this test is supposed to fail, then it's considered to find a bug. And then it writes out a nice bug report, which basically outlines what was the property that failed, what's a minimal reproducible example, and some explanation of the bug. So this is basically the agent workflow, and really the agentic part is in this self-reflection loop. Otherwise, it's just like a series of steps, but the agent is basically autonomous in terms of it has to convince itself that this test justifiably fails and that it is a real bug. Obviously, we give it some like rubric to evaluate this. So the self-reflection loop, so the agent has to reflect and triage both passing and failing tests. So if a test fails, the assertion may be wrong, right? It may have hallucinated an incorrect assertion, or it may not be fully grounded in the code, or it's invalid inputs. For example, the test may, so when you, in hypothesis, if you pass floats to the function, it also tries nan and infinity. But if the function wasn't meant to explicitly handle nan and infinity, then it's kind of an unfair thing to test. So this is one of the things that the agent will catch when it like reflects on the code once again. Or there may be like numerical errors because the floats are subnormal. These things should be generally avoided in tests. If a test passes, it may simply be because it's too loose. Like the assertion that it's testing is just, it's not actually testing the property that should be there. And then the agent refines the input domain and or the property. And one interesting thing that I'll note is that the models are getting much better at correcting themselves, in the sense that we did observe a notable improvement from Sonnet 4 to Opus 4.1 to Sonnet 4.5, which is Sonnet 4.5 is the newest model. So here's some examples of self-reflection that we've observed. One example that we've observed is that the agent wrote a test where basically the entire test was wrapped in a try-catch block. So obviously when the test fails, this assertion error gets caught, and then actually the test passes. And so then after the agent reflects on this quote-unquote passing test, it realizes this, and then it deletes the try-catch, and then it realizes that it was actually a bug after all. Another example is that the agent writes a test with an inappropriate input, which should never go to that function. And then it realizes this after further analyzing the code, and then it changes the input domain. So this self-reflection step is quite important, especially in terms of lowering false positives. Because if this is going to be useful for developers, we don't want to spam them with like hundreds of incorrect bug reports. So I will get to this later. So now I'll talk about our experiments, taking this agent and scaling it to run against basically 100 popular Python packages. So we curated a diverse set of them. Some of them were taken just based on like top number of downloads from PyPI. Some of them were taken from just like our familiarity with them. And this spans a variety of domains, for example, numerical computing, databases, cloud computing, etc. So we called the agent on each of these at the module level. So for each of these packages, we took one module, like one level deep, basically. And we used a variety of approaches to rate the bug reports, which I'll get to. Now, the most important thing in this whole process was maintainer validation. Because even if the LLM says it's correct and so on, the ultimate validation is getting it approved by the maintainer of that package. There's a few reasons for this. One reason is that not all bugs are important enough, and some maintainers will just get annoyed if you report some super minor bug, because the maintenance burden is actually higher to fix the bug. Another reason is that, and I'll show some examples of this, sometimes the LLMs just totally misunderstand the intent of the code. And so if you report a bug, the developer will be like, oh, I meant it to be like that, and like, or I never meant it to be called like that, for example. But that was not clear in the code. So we also tried to get maintainer validation on the bugs that we found. So now, so the first set of experiments that we ran was with Opus 4.1. This is sometime in the summer. There were two criteria by which we rated the bug reports. So after we ran them on the 100 popular Python packages, I think we got around 900 bug reports. And so we used two criteria to evaluate these bug reports and filter them. The first was, is this a valid bug? And the second was, is this, would we report this? So this is stronger criteria than just, is this a valid bug? For the reasons that I just explained, like some bugs are literally just too minor, and maintainers do not want to deal with them. So based on these questions, we developed a rubric that ranks these reports out of 15. And then we passed each bug report and the rubric to Opus and got it to rate all the bug reports. Then we took the top scoring reports and we actually manually went through all of them and rated them on these two questions. And I would say that this rubric was actually highly effective. Of the top scoring reports, we would say 86% were valid bugs, and 81% we would say are valid and reportable. So this is quite useful because, again, we don't want to give a developer like 900 bug reports. So it's quite useful to have this like post filter step. Now, this set of experiments was quite different than the Opus experiments. So Sonnet 4.5 came out mid-September or end of September or so. And in the weeks leading up to it, there were a bunch of internal evals being run. And actually, one of the internal evals that people were running was on this task to see how good it is at this bug finding. And so the internal eval that was run on Sonnet was basically we ran on a subset of 10 packages, just like 10 very popular packages like NumPy, Pandas, etc. And then instead of that rubric step, we instead had a second agent, which was basically supposed to evaluate the bug reports and also have access to the code base and so on. And that agent used Sonnet 4.5. After the second Sonnet rated the bug reports for severity, we then sent the high severity bugs to 3 different human experts, human expert programmers, who we paid to evaluate them. And then they would rate them for severity and whether it was a bug or not, as well as their confidence in that question. So that was the Sonnet experiments. So yeah, it's harder to have numbers for the Sonnet experiments. So what I would like to show now is we've actually reported a few of the bugs that these 2 experiments yielded. And actually, many of them have been accepted by maintainers. We also submitted patches for a lot of them. And they have been now merged into some big packages like NumPy, SciPy, etc. So I've made a website where you can browse all the bug reports as well as like the reviews and ratings and so on. So yeah, now I would like to show the website. Just one sec. Yeah, so this is the website. I'll have the link at the end if you want to browse it yourself. So we have the 2 sets of bug reports here. So these are the Opus ones. And you can, for example, view the bug report. So this is the bug report that was generated for, this is an AWS package. Basically, it was like mishandling dictionary keys, and it loses. And the way that Sonnet caught this was actually Opus caught this was writing a round trip property. There was like basically a decode encode function for dictionaries in this AWS package. And then we reported the fix, and it has now been fixed in this package. This is one of the interesting bugs, in my opinion, which is this NumPy bug. I find this interesting because I fixed it. So the bug was basically that if you were drawing random values from the walled distribution in NumPy, sometimes called the inverse Gaussian distribution, you sometimes get negative values. But the property of this function should be that it always returns positive values. And so I looked into the C code for this, and I realized that they were using some numerically unstable calculations. And I basically proposed a different algorithm for it, and now it has been accepted into NumPy. Here's an example of a bug that was rejected, actually. So dateutil, the property that Opus wrote for this was that Easter should always be on Sunday. And it found a year for which Easter was not on Sunday. Like there's an algorithm to compute the day of Easter for any given year that dateutil uses. And so my collaborator Liam, he reported this bug. However, they said that it's due to a difference in calendar systems, and that's why it doesn't end up on Sunday in like I don't know, 2,000 years ago or something like that. So that was rejected. So as you can see, sometimes the LLM obviously does not understand the full intent of the code. Like this issue with the calendar systems was not mentioned in the code, so of course it couldn't know that. But I think that as a developer tool, if you were the dateutil developer and you were trying to use this tool, you would obviously know that context, and you could like further prompt the agent and so on and direct it so that it wouldn't make these mistakes. Here are the Sonnet reports. So the Sonnet reports have some more detailed analysis because we ran that evaluation agent, and then we also paid these human reviewers. So here's a SciPy bug, for example. It was rated severity high by the evaluation agent, and then we sent it to the human reviewers. You can read their reviews on it. This is their write-up about the bug and whether they think it's a bug or not, and would they file the bug or not. So yeah, and then the same status as you can see here. So this SciPy bug has been fixed now. This pandas bug has been accepted as a bug, but I don't know how to fix it. So yeah, but I did see someone else trying to fix it, so that is in the process. Yeah, so there's a bunch of still like high severity bugs here that we haven't reported. So there are also like, yeah, so Sonnet, I would say, actually found some like deeper bugs than Opus was able to. For example, Sonnet was also able to find some security issues. So one example of that is there's this cross-site scripting vulnerability in the fast API package. So obviously the severity is rated high and all the human reviewers agree, but we haven't reported this one yet. So yeah, I mean, we are certainly open to people like reporting these bugs or fixing them themselves if if you want something to do. Yeah, so yeah, that's all for the demo. All right. Oh, okay. Thanks. Yeah, so to sort of wrap up what I've just shown, so we all know that language models demonstrate strong code understanding ability, and we have shown that they can find and test high-level properties of code. Our agent found hundreds of important bugs across the popular Python libraries, which we're still in the process of reporting. Obviously, there is a dual use problem here. So there's a possible malicious use, which is autonomous discovery of vulnerabilities. For example, I just showed that it found that security vulnerability. However, we believe that as LLMs get better and cheaper, agentic PBT could become a valuable component to traditional testing. And let me just insert some of my own personal opinion here, which is that, so I do think PBT in general is quite underused by the developer community. I guess it's not really taught, in programming classes and so on. But ever since Zach taught me PBT, I can't imagine myself testing software without PBT. And now almost any code I write, I try to write property-based tests for it. And I find it very valuable. So even if you're not using LLMs to write PBT, I would encourage everyone to explore them for their code. And here's some links, which I'll just leave up also during the Q&A session. So you may be wondering how to use agentic PBT in your own code. The agent that I just presented is specifically like sort of aggressively targeted towards finding bugs. If you just want to write good tests, you can use this variant, which we've just released on the Hypothesis website. So this you can like easily plug into your own repo using Claude Code, and then it'll get you started writing good PBT tests. This is the website to browse the bug reports if you just want to look through them, or if you're interested in reporting or fixing them yourself. Actually, I think it's quite good practice to fix some of the simpler bugs. And then lastly, here's the paper, which was accepted at a NERVS workshop. So I will be presenting that in San Diego in a few weeks. Yeah, so I'll leave these links up. And now I'm happy to take any questions.
Okay, we'll actually have a 3-minute break if people want to go to the washroom or something. But yeah, I would encourage submit any questions you haven't yet to the link in the orange posters and vote on the other ones there, and then we'll do a sit-down Q&A in 3 minutes. All right, let's get into it. Yeah, feel free to continue submitting questions or voting on them. Always very helpful to me to know which ones people want to ask most. First, you didn't tell us too much about yourself. How did you get involved in the field? What's your background in terms of?
Sure,
everything?
yeah. So I just finished my PhD at the University of Toronto. I just defended at the end of August.
Hey, congratulations.
Thank you, thank you. Um, uh, and my thesis and my work was on formal verification. One of the most influential classes that I took during my PhD was a class in the comp sci department, which is called automated reasoning. And it introduced me to all these concepts like Z3 and other formal verification tools. And so I did my thesis on formal verification of machine learning. That's how I became interested in like the intersection of them. And yeah, that's how I ended up working on AI safety, and then that's how I ended up at Anthropic.
Cool. And this seems like I imagine this is a lot more kind of hands-on in the weeds than the thesis work. Is that accurate or?
And in what sense?
Oh, I guess when I I mean, maybe this is just my naivety because I'm outside the field in terms of like I don't have a STEM degree, but I imagine like PhD thesis being a lot of like more theoretical work, whereas this was like you're just getting an agent to successfully find bugs.
Yeah, I mean, I think I did a mix of theoretical and applied work during my PhD. So like, yeah, a lot of the theoretical work that I was doing was developing algorithms, but then I also would like implement the algorithms and test them and so on.
Okay, so it wasn't so much of a jump. All right.
Yeah. Although I would say like this has like almost no theory. This is like pretty much all,
Yeah, that was the vibe I
empirical.
got from it.
Yeah.
Cool. All right. So, number one question that inquirer minds want to know: are you worried about adversarial uses of this approach? Like, it seems like you wouldn't need too many tweaks on this. Actually, almost none to like find the bugs and then exploit them instead of report them.
Yeah, that's a good point. And if you read the Anthropic post from today about the cybersecurity attack that they found, which is using Claude Code, they made a diagram of what they believe the agent was doing, like the agent workflow. And honestly, it looks very similar to that diagram that I showed. I mean, but instead of like writing the bug report at the end, it would go to like a phase 2 agent where it was trying to exploit that vulnerability. So yeah, it is definitely a real risk. However, I would say that also like this empowers the developer. If you're working on some code base, you can like use this as a check before you release it in the public. And I guess that's the problem with like any security scanner or anything like that. It can be used by malicious people, but it's also often used by the developers themselves.
Yeah, but is this something you think about when you're designing it? Are you are you just like purely thinking about like, okay, how do we find the bugs and report them? Or like, is this something that is also in the back of your mind while you're designing it? Like, okay, like, do we also want to kind of tweak the workflow or the instructions of the agent such that it's like harder to use it that way? Or are you just kind of like, well, that's what the adversarial robustness team needs to deal with Claude, and that's kind of their domain?
Yeah, I mean, I don't think there's a way to separate those two uses. Like, I think if it's good at finding bugs as a helpful thing, it's also good at finding bugs as a harmful thing. I don't think there's a way to like distinguish them. So unfortunately, yeah.
Okay.
Yeah.
So basically, you want just the agent to appropriately refuse when it realizes it's doing something bad, which
Yeah.
I guess is a little outside what you're doing. Yeah.
Right. Yeah.
Or could you get a little bit more detailed for us about like how you give the instructions? Like you had these like 5 steps that the agent takes, including like the steps I think 3 and 4 were in the loop. Like what does that look like? Okay, so I actually haven't messed around with any kind of with Claude Code and Agentic sense or anything. Like what does that look like? Do you just like have a really good detailed prompt in there for each of those 5 steps, and then it connects to some MCP tools? Can you get a bit more detailed on how that's done?
Yeah, sure. So essentially, it is operationalized as a Claude Code / command. So at least for the experiments that I was running for this like bug finding, I call that / command hypo because I don't want to type hypothesis every time. So you just do like / hypo, and then you write out the name of the target, like / hypo numpy, and then it would target numpy. In this article, this is basically a Claude Code / command for just writing good tests. And I think the command here is / hypothesis. So once you download this and you store it in your .claude folder, then you can like run this on any code that you're doing. But it basically is like a Claude Code command, and it has like various tools. Well, the tools are rather basic. It's like read, write, and bash. Yeah.
Right. And then any of the steps were they like particularly like I don't know easier or harder than you expected?
Reducing the false positive rate was probably the hardest part. I mean, it's pretty trivial to get like a simple prompt working to like do this vaguely, but getting it precise and getting it working well and teaching it how to appropriately triage bug reports and that sort of thing, that probably was the hardest part. Yeah.
And that would be in the loop between steps 3 and 4. Yeah?
Exactly. Yeah, that's like the self-reflection loop. So that was probably the hardest part. Yeah.
All right. Now, I understand this work was like being done by Anthropic, but just out of curiosity, did you guys try this with any of the other AI systems and compare them to like how it works with, ChatGPT or something?
Unfortunately, no, but you can put this markdown file into other agent frameworks as well if you don't use Cloud Code, if you use Codex or something, yeah.
Okay. And then all the examples you gave, I believe, were Python code specifically, right?
Yeah.
Yeah, like how much of a leap is it to like point it at like Java code or something? Is it pretty plug and play?
Yeah, so there's two elements at play here. The first one is that it has to have a good enough understanding of that programming language in order to infer the properties and so on. So probably, yeah, for things like Java, Rust, etc., it's probably like pretty good at that. The second thing is there needs to be a property-based testing framework for that library. So for example, in Hypothesis, in Python we have Hypothesis. The first ever property-based testing library was in Haskell, which is called QuickCheck, and then he's excited by that. But then it was ported into various other languages. To my knowledge, there is one in Java. I don't know about other languages, but yeah. So those are the two things that you need in order to apply this agent to other languages.
It sounds like most languages, most of the big ones will have that.
Probably. I also don't know how sophisticated they are. So I would say Hypothesis is like really well built and really well maintained. Yeah, Zach puts a considerable amount of effort into it on top of his full-time job, which I don't know how he does. So yeah, I don't know like how well the Java one works, for example, but yeah.
Okay, so yes, with some caveats. Cool. Can the agent deal with code side effects? For example, like accessing the file system?
Like the agent accessing the file system?
I don't actually understand this question. I just read it off. Giles, you want to clarify?
Like if the code itself causes side effects in the file system? That's a good question. Yeah, I mean, I guess it would depend on if the agent realized that that was something that was going on and it could write a property about that. Yeah, like for example, it could assert that like no new files are created or something. Like that could be a property to test whether there's some file system side effects. So yeah, in theory, I think it could happen if it realizes that that is something that it should test. Yeah.
Can you speak a bit more about like costs? Is this something? You stated before that this could become something that like developers just use as part of their standard. Like, oh, you're making code, then the kind of final step is going to be pointing whatever version of Claude at this. Like, how expensive is it? Is that quite plausible that like in very very short order, like next year, this would become a standard thing, or is it still pretty computationally expensive?
Yeah, that's a good question. So I didn't talk about cost. So to run the Opus experiments in total cost around $6,000 in Claude API calls. And if you get the cost per real bug, it's like $8 per bug. So yeah, if you're a developer, I don't know if you're willing to pay $8 per real bug.
Well, but like $8 for like bugs that you guys ended up submitting and like the maintainers approved, or $8 for like the bugs, $8 per bug, which was then whittled down.
Oh no, this is $8 per bug that we we ourselves verified as correct.
Okay.
Yeah. So like there were around like 900 bug reports or something like that. So but not all of them are real bugs. I forget the exact number of real bugs, but eventually, all things considered, the cost came out to $8 per real verified bug.
Okay,
yeah.
That's quite promising then, actually, because I would expect that this is like the first version of this, right? That presumably costs will come down over time.
Exactly, and I should also note that Opus is 5 times more expensive than Sonnet. And then afterwards, we tested on Sonnet 4.5 and found it to be performing at least as well as Opus. So you can get that cost like 5x down for real.
Oh, so we're talking like $1 to $2 a bug with current version.
Yeah,
probably.
yeah.
Okay.
I would estimate that.
Right, and like how much How much space for improvements? No. Okay, so like one way you can make that cheaper is by just like having the cost of inference come down, right?
Right.
The other way you can make it cheaper is by like writing a better version of it that's just more efficient at finding the bugs. Like how much space is there for that?
Yeah, that's an interesting question. Like we spent a lot of time developing the command and like testing it and so on. Yeah, I'm not sure what areas of improvement there are in the command itself or in the prompt itself now. I mean, maybe there could be, but it's obviously hard to search in like a discrete space.
Yeah, I don't even know how you'd begin like trying to measure that. And well,
Yeah.
I guess you could give it a measurement, but like I don't know.
Right, yeah. I mean, one thing is probably, I don't know, maybe more sophisticated, like reproduction or something. Like tell it to try to reproduce the bug more, rigorously or something. Yeah, because I think the main thing that we're concerned with is again like getting valid bugs. Like it can generate like a ton of trivial bug reports or something, but we want them to be valid.
Yeah. Okay. Right. Yeah, it's interesting. There's like quite a few dimensions you got to be thinking about when you're thinking about how to optimize it.
Yeah.
Okay. So far we've just been talking about like finding bugs. To what degree can this also be applied to just finding like improvements in the functional aspects of code, or is that like a whole different ballgame, or is that like we could just make a couple tweaks and it could do that?
Yeah, I mean, so the prompt in this post, which is like a more general prompt, it's not meant to find bugs. It's just meant to write good tests for you as a developer to just get started. This is like, I don't know, it's sort of a modification of our like bug finding prompt. Mainly, we have to remove some of the like stuff about triaging bugs and that sort of thing. I would say that it's quite useful. I have already started using this. For example, like I'm working on this linear algebra library for fun, and obviously there's all sorts of like mathematical errors that can arise. And so I just get this like Claude Code agent to like write out those mathematical properties as property-based tests, and then test whether like all my matrices are fine and these sorts of things. And it's actually helped me find all sorts of like implementation issues when I was like writing out the algorithms for my functions. So yeah, I would say like it's quite useful. I would say for the developer. Yeah.
And then jumping back, okay, let's talk in a bit more detail. You talked about you would look at like one module at a time. Okay, so for those of us who aren't super technical, what's like, can you describe a module compared to?
Oh yeah, sure. In Python, libraries have modules. So there's like the Python library NumPy, and then it's organized into submodules like numpy.random, numpy.linear algebra,
like how many
etc.
modules would be in NumPy, for example?
I think the first level modules in NumPy, I think there are about like 20 of them, maybe, if I remember. Yeah.
Okay.
It really depends on the
yeah,
library.
it's not like 3, it's not like hundreds. It's like, or I guess some of the smaller libraries.
So some of the cloud computing ones can easily go into the hundreds for some reason. I don't know why. So that AWS one was really a pain to test, but yeah, it really depends.
Okay, so high variance there, and then okay, and then how long will it generally take to like go through the entire loop for a given module?
Yeah,
is there a lot of variance there, like, or
it would pretty consistently take around like maybe 8 to 10 minutes per module. So we had like 100 libraries, so easily like thousands of modules. And then so obviously I had to run the agent in like parallel if I was gonna finish in time. So there are like multiple agents working at the same time so that everything could be done in an efficient manner.
Right. Okay, but like 8 to 10 minutes per module is not like, if we're talking the average, okay, but like you can basically leave it overnight and it'll get a considerable amount of work done. It's not like you.
Yeah. So the other thing I would say is like if you're actually using this as a developer, I would suggest to be more specific than just doing like every module or every like first level module, because you as the developer know better how the code is organized and so on. And so you may know like, okay, I want to focus my efforts on numpy.random or something if I'm the NumPy developer, and I don't want to waste my time on like numpy.core, which is probably very well tested. That just has like the basic addition, subtraction type of functions. So yeah, if you're the developer, you can probably like guide the agent more carefully, and also probably get better cost effectiveness out of that.
Okay, one underlying, I guess, kind of like, you were really excited to share with us the wonders of PBT, and I guess like some people agree with you, and but like it seems like it's not super widespread or adopted yet. Is that correct?
Yeah, that's right. That's right.
Do you see that as being a barrier for like this type of method being adopted, or do you think this is like actually maybe the way that people end up being drawn to PBT?
Yeah, I see this as a way of popularizing PBT because I think one of the barriers is like people, even if they know the concept of PBT, they probably haven't written it before, or they don't know how to think of these properties and so on. But here, the LLM can basically help them get started.
I guess they don't even need to know about it. They just need to know this agent finds bugs.
Yeah, to be honest, you can just pull up Claude Code and just /hypothesis and just come back 10 minutes later.
All right, fair enough. All right. So people are going to adopt PBT without even knowing what it is. Great. Cool. Can you tell us a bit more about like the proportion of tests here? Okay. Like, do you know? Yeah, I'm very curious if you can go into more detail about like how often does it find false negatives and false positives and then correct itself, and then for when it actually like shows you guys their work. I think you said it was something like 86% were legitimate bugs, and then 80% were legitimate reportable bugs.
Mm-hmm.
But was that like during the loop process? It was like, I don't know, it would find like 100 bugs, like 50% of it, and they later decided were like not bugs. Or could you speak a bit more to like how that worked?
Yeah, I mean that's hard to quantify because you need to read the transcripts of the agent.
You didn't do that?
Sorry?
You didn't do that?
I mean, I read some of them, which is how I found some of those examples. So I don't have concrete numbers on how often that reflection happened.
You could train an agent that will do that for you.
That can read that. Yeah, that's true. Yeah.
Okay, so you're not sure.
Yeah, I'm not sure. Yeah, but although in my observation, it does try to reproduce every bug that it thinks it found. Yeah.
Okay, gotcha. Yeah, and do you have any intuition on like whether most of the work was actually basically cutting down the false positives, or?
I would say it's probably because like in the rest of the prompt it mentions finding bugs and so on. I feel like it's biased towards analyzing the possible bugs more carefully.
Oh, it's just got the word bug so many times in this context. It's just going to be a little overeager.
I think so. I mean, we instructed to test like to look at passing tests and failing tests, but at least in my observation, it seems to try to be more careful with the failing tests to see if it's a real bug.
Is now I'm wondering, is there any mechanism for it, like on multiple passes, finding bugs you didn't find earlier? Because I have an easy time imagining how it goes through its multiple steps. It does step 3. It I've generated all these bugs, and step 4 is analyzing those bugs. But it kind of seems like if it doesn't catch a bug on first pass, it's not going to catch it in the iterations later on. Is that more or less correct?
Well, it can catch it because it may reflect on a passing test, and then upon further reflection, it realizes it's supposed to fail, and then it finds a bug. So there was one example in the presentation, which was it basically wrapped the entire test in a try-catch block, which basically means that even if the test fails, the function actually passes. So to it passes. And then it analyzes that, and it realizes, wait, I wrapped the whole thing in try-catch. That's making it pass. It deletes that, and then it realizes this is a bug.
Okay, yeah, that makes sense.
Yeah.
Why haven't you reported the cybersecurity bug that you said was serious? That seems like that's something you would do right away. Are you guys just really busy?
I actually just found it last night.
Oh, okay. All right. Fair enough.
I didn't go through all 2,000 bugs
for this event first, and then now you're.
I was looking for interesting examples of bugs for the presentation, and then I found a cross-site scripting bug. But yeah.
Great. It would have been great for us here if that it gotten exploited in the meantime. As another example. Yeah. Okay. All right. Well, maybe one of us can report it now that you've shared the website with us. All right. Cool. Yeah, no, that was. Are you down there sharing your slides with people after this is done?
Yeah, for sure. Yeah.
I imagine most of the information should be in the post.
Yeah, most of the information is in the paper, as well as the accompanying website.
Okay, and do you have any advice for someone who's early in their career? We have someone someone for looking for a QA engineering role.
I don't know. I feel like it's hard for me to give career advice.
As someone who's very experienced and well into his career, yeah, that's right.
I mean, yeah, I also just started my career, so yeah, I don't know. I guess I've always just done things that I'm interested in. Right. Yeah.
Get a PhD at U of T and do the Anthropic Fellows program. That's a good way to get a job. All right. All right, cool. Thanks so much, Maaz. Really appreciate it.
Thanks, Mario.
All right, everyone's welcome to stick around until we kick you out, but it's generally at least an hour or two. Thanks.